Exercise number 24 asks us to differentiate the function y equals the square root of x plus x, all divided by x squared. So the first thing you should notice when looking at this is that it is written as a quotient. And if you read my notes, you saw my very emphatic warnings that we do not yet have a rule for handling derivatives of quotients. That will come in the next section. But we can take the derivative of this if we perform some algebraic manipulations first. And the same principle applies to products. If you can rearrange it into a form that we have the tools to deal with, then you can go ahead and take the derivative accordingly. So something we note here is that this quotient can be easily rewritten because the denominator is a single term. So we could split this up into a sum of fractions, simpler fractions. So we have the square root of x divided by x squared plus x over x squared. And if we simplify this a little bit, the square root of x is x to the 1/2. So applying the rules for quotients of powers, x to the 1/2 divided by x squared will be x to the power of 1/2 minus 2 is negative 3/2. And we have x divided by x squared, that's x to the first, so that is x to the negative first, right? So y is equal to x to the negative 3/2 plus x to the negative first. We could have also gotten here by saying that we have the square root of x, that's x to the 1/2, plus x to the first in the numerator, and we could rewrite the division by x squared as multiplying by x to the negative second, and then distribute this in, and that will get us to the same result. You might find this to be a little bit quicker if you're comfortable working with exponents that way. Whichever way we do it, either passing through here or splitting up the fraction, we get to this expression for y. Now, we haven't done any calculus yet. This is all just algebra, right? But what we have done is rearranged this quotient, or product, as now being a sum of two terms, and each term is a power function, x raised to the power of a constant. So now we can take the derivative, dy by dx, which you could also write as y prime. We can take the derivative of each term in turn using the power rule. So we have x to the constant power of negative 3/2. So we have that power, negative 3/2, times x raised to that power minus 1. Negative 3/2 minus 1 is negative 5/2. We would have plus, but we're about to add the derivative of this, where this power comes out front as a multiple. So that is a negative 1 times x raised to the power of, always subtract 1 from the exponent. Negative 1 minus 1 is negative 2. And here we have one expression of the derivative in question. Negative 3/2 x to the negative 5/2 minus x to the negative second. Now, the original expression was written with radicals and fractions, so if you would like to retain that form, you could do something like negative 3 over 2 times, we have x to the negative 5/2, so that would be, we could pull out an x squared radical x. I believe that'll work out fine for us. Minus 1 over x squared. So this would be another way you could write the derivative if you preferred to have the fractions and radicals rather than negative and fractional exponents. If you wanted to bring this into a single fraction to combine that back together, of course you could put this over a common denominator. We're missing the 2 radical x in the second case, so we could write this as negative 3 minus 2 radical x divided by 2x squared radical x. This would be another way of writing the expression. Normally, I would say just stop with this first one. This is perfectly good. Sometimes you may find it easier to rewrite it in a different form depending on what you're trying to do with it, any further computations, or maybe it's easier for you to look at, whatever. But typically I would say that this first form is the appropriate place to stop and the best way to go. Any of these three that I've boxed here would be considered fully simplified in my book. So that's all we had to do in this problem. You can see that by algebraically restructuring things, we were able to apply just the very simple rules that we know. Just to illustrate one more step of how these derivatives would go. So again, this is all that this problem is asking for, but just to take a little bit further for the sake of illustration, suppose we wanted the second derivative of that function. So that would be y double prime, or d squared y by dx squared. And to take that derivative, of course, we want this first form that has this as a difference of terms with the power rule. We don't want to have to deal with quotients. If you had something like these latter two, you would have to turn it back into this. So let's use that form there. Taking the derivative of the first term, we have, actually let me go ahead and write this out because there's a lot going on here. So I'll write out what we're doing. We have this constant negative 3 halves. Now we bring out the negative 5 halves, bring that out front, and subtract 1 from the power, so that's a negative 7 halves. Minus the negative 2 comes out front, and we subtract 1 from the exponent, that makes a negative 3. And of course we always want to simplify and clean this up, so it looks like multiplying those we have 15/4 x to the negative 7 halves plus 2x to the negative 3rd. So this would be the second derivative of the function y that we were given. Again, not what this question asked for, but just to give another example of how we can apply this power rule. We basically just take the whatever we're taking the derivative of, the exponent pops out front, and then we subtract 1. So this negative 5 halves comes out front as a multiple, and then we subtract 1 there. Again, go through the illustrations and proofs in the textbook for why that's the case. There are a couple of different ways that we can see that algebraically from the definition of the derivative.